So we're going to switch things up a little bit, because when we dealt with the translational motion piece, we started by doing the dynamics part first, so focusing on using Newton's second law to solve for the acceleration, and then we came back in and added kinematics. Here we'll flip this around, but it's the same basic idea that it's not like these are fundamentally two different problems. Both of these pieces, the rotational dynamics and the rotational kinematics, are how we keep track using Newton's laws objects as they rotate. Again, we're going to focus on two types of motion just like we did with translation motion. We're going to focus on motion with constant velocity, and we're going to focus on motion with constant acceleration. And so with constant velocity, we said there's really only one equation for translational motion, and that's just x equals x naught plus vxt. So when you have constant velocity motion in the x direction, this is the equation you have that describes it. Well, the same thing's true in rotational motion. You have a single equation. And notice there's only a couple things that's changed. One thing is that we just swapped out letters. So instead of x position, we've got angular position. Instead of translational velocity v, we've got angular velocity omega. The other thing that's changed is this is motion in the x direction. This is motion about the z-axis. Now, one last change that we'll make is, because again, as a general rule, we very rarely care about the angular position of something. What we do care about is how far it's rotated through. And so we'll just go ahead and reframe this equation into thinking about the angular displacement, because that's almost always what we're actually interested in. Now, for both of these, again, we've built in the idea that it's constant velocity. So here it's constant translational velocity, here it's constant angular velocity. And so what this means is this equation is only valid when your acceleration equals 0, and this equation similarly is only valid when your angular acceleration equals 0. So the second type of motion that we set up was motion with constant acceleration. Again, with translational motion, we said that there were three equations. And again, here we've chosen to just limit ourselves to writing them out in terms of those three equations in the x direction. But of course, these could be true for x motion, y motion, z motion. So motion along any of our three coordinate axes. We had an equation that gave us the position as a function of time. We had an equation for the velocity as a function of time. And we had an equation where we had eliminated time, and so this sort of related all of our other variables. Again, assuming we have constant acceleration, we have a very similar set of equations. So there is an equation for the angular position with respect to time, for the angular velocity with respect to time, and then again an equation where we've eliminated time. And so again, this is basically in all of our other variables. Notice motion in x, angular motion about the z-axis. Just like before, because we're almost always going to be more interested in the angular displacement than any final or initial angular position, then we'll go ahead and rewrite these equations in terms of the angular displacement, so delta theta. And so here basically are the three constant acceleration equations for rotational motion. Just like before, these equations were derived assuming the acceleration was constant. So if the acceleration is not constant in your problem, these equations won't help. These rotational equations similarly were defined on the idea that the angular acceleration is constant. So there's the equations that we're going to use. In terms of working a rotational kinematics problem, again, our thinking is going to be very similar. So we're going to start by saying, what do we know? And again, here we're interested in sort of four vector quantities and then again our scalar time. So the angular acceleration, the initial angular velocity, the final angular velocity, and the angular displacement. The next question is going to be, is the angular acceleration of the object 0? If it is, then we know we really just have a single equation. If it's not, then again I need to ask, is my angular acceleration constant? Because if it's not, then I can't use any of the three constant acceleration kinematic equations that we've set up. If it is, of course, then I need to figure out which of those three equations I want to use. So the next equation, do I know or want to know time? So again, if I don't think I need to deal with time, if I think I can get away without worrying about time, well, I've only got one equation that doesn't involve time, so I might as well try it out. On the other hand, if I know I have to deal with time, whether it's because I was given time as a variable, it's what I'm asked to solve for, then again it becomes a situation of do you know more about the angular displacement or about the angular velocities? And so if I know more about the angular displacement, then I probably want to use the displacement as a function of time, that equation. If I know more about the angular velocity, then I want to use the angular velocity as a function of time. It's the same basic thinking in terms of figuring out which equation is probably going to be the most useful to use as we're working through a problem. As an example, let's think back to a kinematics problem we would have worked for translational kinematics. We've got a motorcyclist who's traveling a long straight stretch of highway. Initially he's traveling at a speed of 25 meters per second. The road sign says he's approaching a small town and needs to slow to a speed of 10 meters per second. If the small town's only 300 meters past the road sign and he slows at a constant rate, what's the cyclist's acceleration? How long will it take him to slow down? And so our process was, he said, well, let's draw out the initial and the final states described in the problem. Let's figure out what our vectors are. So I've got an initial position vector that's 0, a final position vector that points in the positive direction and has a magnitude of 300 meters. I've got an initial velocity vector that points in the positive direction, has a magnitude of 25 meters per second. A final velocity vector that points in the positive direction has a magnitude of 10 meters per second. The acceleration, because I know my object is slowing down, the acceleration has to point back in the negative direction. So I can set up my table showing what we know, and in this case I know the values for my initial and final velocity, I know the values for my initial and final position. What I don't know is how long it takes and then what the acceleration is, but I do know that the acceleration has to be negative. So when I solve for this I better get a negative answer for that value for A. I have two unknowns. Oddly enough, I'm asked two questions. Those questions line up really well with my unknowns. What are the acceleration, how long, or what's the amount of time that it's going to take him to slow down? So now I can go through and solve for them. So if I want to solve for the acceleration, well, I can choose to say, well, I don't know time, so let me see if I can get away without knowing time. And so I use my v squared equation, solve that for the acceleration, plug in, sure enough I've got everything I need, and I get an acceleration value that's negative 0.875 meters per second squared, and that negative is consistent with the value that I knew that I needed. For time, well, now that I know basically everything else in the problem, I've got a choice, and I'll choose to use the velocity equation because of course it's linear rather than quadratic, and so in this case I'll solve for time, plug in my values, and I get a time of 38.6 seconds. All this was the process that we used in solving a translational kinematics problem. Guess what? Very similar process. So let's take a rotational example. And so now what we're going to say is we've got a food processor. Its blade can spin at variable speeds. Initially the blade's spinning with an angular speed of 25 radians per second. You switch the processor to a slower speed of 10 radians per second. The blade rotates through 30 radians as it slows down, and it does so at a constant rate. What's the angular acceleration of the blade? How long will it take the blade to slow down? So again, we're going to start by drawing two pictures, one showing our initial situation, one showing our final situation. And the big difference, of course, is simply that they're still spinning in the same directions. It's just spinning more slowly at the end. Using my right hand rule, again, I take my right hand, curl it in the direction in which the blade is spinning, and I've drawn it spinning counterclockwise here, which means that the angular displacement is going to point out. The initial angular velocity, that points out. The final angular velocity, that points out. And because I know that my object is slowing down, that means the angular acceleration has to point in. So in terms of the four vector quantities that I'm going to need to deal with here, I know which way they all point. I now get to pick a coordinate system just like I did before. And so I'm going to let the positive z direction point out, which means that when I think about what I know, the initial angular speed, the final angular speed, and the angular displacement are all going to be positive quantities. They point out, and I said out was the positive z direction. Time I don't know. The angular acceleration I don't know, but I do know that it points in, which means that when I solve for it, I better get a negative. Again, I look at this and I say, well, I got two unknowns in my problem, and each of them line up with the two questions I'm asked to solve for. So what's the angular acceleration of the blade? Go solve for alpha. How long will it take the blade to slow down? Go solve for time. So again, I can take the information I've got and play the same game. So if I want to start by solving for the acceleration, I know that I have a non-zero constant angular acceleration. I don't know time, so I'll see if I can get away without knowing time. And sure enough, when I solve for alpha, plug in all my numbers, I get a negative 8.75 radians per second squared. And again, I like the fact that that negative's sitting there because that's consistent with the sign I knew I needed to get before I started doing any math. Now that I know alpha for time, I could use either of my two functions of time. And of course, because the function of time for the angular velocity is a linear equation rather than a quadratic, I'm going to use that one. I solve for time and I get the time is 3.86 seconds. Hopefully what this is highlighting is the process in working our kinematics problems for rotational motion are going to be exactly like working one-dimensional kinematics problems back when we did translational motion. So you want to go through that same process of drawing yourself a couple of pictures, picking a coordinate system, drawing in those vectors to figure out which signs you're going to need, figuring out what you know, walking through to figure out which equations are going to be helpful in terms of solving for what you don't know.